In this video, we're solving a resistor network circuit where we have some resistors in parallel and in series, and we're going to use the parallel and series resistor rules to simplify this thing down to a single equivalent resistor, and then we should be able to answer any question that we're given about the circuit. So when I look at this circuit, I have an ideal power source of 9 volts, and then I have a 10 ohm resistor and a 5 ohm resistor. Those are clearly in series because the current has no other option but to travel through both of them. Then the current is allowed to split at this parallel branching where I have 2 4 ohm resistors in parallel. And then finally I have an 8 ohm resistor in series at the end. And we're back to the ground side of the battery. So the way to start here is to simplify the parallel combination of the 4 ohm resistors. And then we'll redraw the circuit. And our parallel resistor combination rule looks like this in general. I have a 1 over R equivalent is equal to 1 over R1 plus 1 over R2. So I plug in those 2 4 ohm resistors. 1/4 plus 1/4 is a half. When I take the reciprocal of that, I get 2. So R equivalent is 2 ohms. And this is a fact you may actually just memorize, that if you have 2 identical resistors in a parallel combination, the equivalent resistance of that is half the value of either one of the resistors. So now we're going to redraw the circuit with that parallel combination replaced by a single 2 ohm resistor. So there's what the circuit looks like when it's redrawn. And now we clearly see that we're looking at 4 resistors in series. And this is the simpler of the 2 resistor combination rules. To find the series equivalent, we simply add together the resistances. In this case, we have 4 of them. So I'll write R1 plus R2 plus R3 plus R4. And that's 10 plus 5 plus 2 plus 8, which gives me 25 ohms equivalent resistance. Now we redraw the circuit one last time. This is now the simplest possible circuit. It's just an ideal power source in addition to a single resistor. And now we can easily get the total current in the circuit. For this, I simply use Ohm's law. If I solve that for I get I equals V over R. And the voltage across this resistor is 9 volts, and the resistance is 25 ohms. And our current comes out to 0.36 amps, and that's the answer to part B. Now in part C, we're asked to find the power dissipated by the 5 ohm resistor. And this turns out to be a relatively easy question. I don't have to go back through the circuit and solve for the current in every single resistor. I just figured out that my total current is 0.36 amps when I simplify it down to the simplest circuit. That 25 ohm resistor came from a series combination, and every resistor in that series combination has the same 0.36 amps running through it. There's no way for that current to split. So it must be 0.36 amps through each of those circuit elements. That means in particular that I have 0.36 amps through the 5 ohm resistor that I'm interested in, and I know its resistance, so I can use the power formula for the power dissipated by a resistor of I squared R, plug in the I, and I find that the power dissipated by the 5 ohm resistor is 0.648 watts, and we're done with the problem. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.